Today we are going to talk about some important operators that are widely used in mathematics and that are really tools in many areas of physics as well. As a prerequisite, I'm going to assume that you are familiar with the different coordinate systems, which are the Cartesian coordinates, which contains the coordinates x, y, z, the cylindrical coordinates, which are like an extension of the polar coordinates, which contains the coordinates r, theta, and z, and spherical coordinates, which contains the coordinates r, theta, the polar angle, and phi, the azimuthal angle. So I assume you are familiar with these different coordinates. So all along this presentation, small f will denote a scalar field, and capital F will denote a vector field. I also assume you are familiar with scalars and vectors. So the first operator that we're going to see here is the Nabla operator, also known as del, which has as symbol an inverted triangle. So the Nabla operator is a vector differential operator that takes several forms depending on the coordinates in which we are using. We are going to see that in a few minutes. So the Nabla operator takes as input a scalar field f and gives you at the output a vector field. This operation usually is given a special name known as the gradient. So the vector field here is not just any type of vector field. We are going to see the expressions. It's a vector that points in the direction of greatest increase of the function. So if we are in Cartesian coordinates, then the gradient has as expression, then the gradient of f has as expression delta f, delta x, delta f, delta y, and del f, del z. So these are just the partial derivatives of the function along the various axes. If we're in cylindrical coordinates, then Nabla f becomes delta f, delta r, 1 on r, delta f, delta theta, and delta f, delta z. And if you are in spherical coordinates, it's a bit more beautiful. Then delta f takes the form delta f, delta r, 1 on r, delta f, delta theta, yeah, and 1 on r sine of theta, delta f, delta phi. Okay. So this is the expression of the Nabla operator or the gradient in the different coordinate systems. So in any case, what this illustrates is that if you have a field, a scalar field, which is f in this case, then what you get, what the gradient of f gives you is a vector, I don't know, that points in the direction in which the function increases the most. So the second operator that we're going to see here is the divergence. That has a symbol Nabla dot. And then in this case, we are applying it to a vector field. So the divergence essentially is the Nabla operator, and you apply the dot product with the vector field you are considering. And what this represents is really the spread of the vector field from a point. So suppose you have a vector field, it could be a stream, you have water flowing in a canal. Let's say at a given point, you have like water that flows. Let me just represent it like that. So what this operation tells you is really how material is flowing from a point, which means that if you're having material that flows outwards from a point, then the divergence in this case indicates an expansion. So a positive divergence indicates a source, meaning you have material that spreads from the point, and a negative divergence will indicate a sink, which means you have like material going towards the point, like a vortex, for example. So this is widely used in fluid dynamics. So if you're in Cartesian coordinates, then the divergence of the vector field F takes the form del Fx delta x plus delta Fy delta y plus delta Fz delta z. If you're in cylindrical coordinates, then delta F becomes 1 over r delta r Fr, like this, delta r, then plus 1 over r delta F theta delta theta, this is theta, plus delta Fz delta z. And if you're in spherical coordinates, the expression is a bit longer, so that's 1 over r squared del by delta r of r squared f of r plus 1 over r sine theta d theta of sine theta f of theta, then plus 1 over r sine theta d f of phi d phi. Okay, it's a bit longer, but these are the various expressions of the divergence in different coordinate systems. So this operation is widely used to study fluid dynamics, because it can really inform us of the evolution, of a fluid in a canal, and enable us to study the behavior, the evolution with time. So the next operator, let me change paper, is the curl, which is essentially a cross product of the Nabla operator with the vector field in this case. So just as the name indicates, the curl operator tells us the rotation of a vector field at a point. So imagine, again, let's say you have a stream of water that flows like that, for example, and it encounters, I don't know, at some point you have maybe a boulder somewhere, or just an obstruction along the canal. Then you can imagine that at this point you're going to have the field that might change like that. So at any given point, we can calculate the curl of this vector field, which is going to tell us how the rotation of the function at any given point in the field. So if we are in Cartesian coordinates, then the curl of f is just the fz. So just imagine taking the cross product of this with the function. F here has three components. If you're in a Cartesian coordinates, it's fx, fy, and fz. And then this has the partial derivatives in each of these directions. So here we are just taking the cross product. So if in Cartesian coordinates, just this minus del fy, del z, del fx, del z minus delta fz, delta x, delta fy, delta x minus delta fx, delta y. So these are the components. Now if we're in cylindrical coordinates, then we can just perform the adequate transformation to get 1 over r times delta fz, delta theta, minus delta r f theta, delta z, delta f r delta z, minus delta fz, delta r, and 1 over r delta r f theta, delta r, minus delta f r delta theta. Okay, and if you're in spherical coordinates, then this becomes 1 over r sine theta times d theta of sine theta f of phi minus delta f theta delta phi 1 over r 1 over sine theta delta fr delta phi minus delta f phi delta r 1 over r dr f theta dr minus delta fr delta theta. Okay, so here are the expressions of the curl in each of the coordinate systems. And the last operator here is the Laplacian, named after Laplace. It's usually known as the Laplace operator. And this operator actually, it has a very special symbol, which is a triangle. And what this triangle represents is actually a double Nabla operator. And actually what's interesting with this operator is that you can apply it to both fields. You can apply it to both scalar fields and vector field. So if Nabla, delta, because this is delta, so delta of f, here you're applying the Laplace operator to a scalar field. That's just Nabla squared of the field, which actually is Nabla f. You remember that the Nabla operator transforms a scalar field into a vector field. So if you want the result of this operation to be a scalar, you actually need to add a dot product with this. Okay, and if you apply the Laplace operator to a vector field, that's b squared of f. But then you remember that if you have a vector field, we cannot apply the Nabla operator to a vector field. We rather need to apply either the divergence or the curl. So what we can do here is to take the curl, for example, of the vector field, and then apply the divergence. So, sorry, we need to take first the dot product, okay, because this is a scalar, and then we want the result to be a vector, so we take the cross products with the del operator. So the result of this is going to be a vector field, which actually represents the second derivatives of, in this case, the components of f. So if in Cartesian, that would be fx, fy, and fz. And in this case, it would just be the second derivatives of f, small f, in this case, the scalar field, in each of the directions, x, y, and z. But that's a scalar at the end. So what this operator really tells us is the diffusion, or the rate of change of the function over time, or the rate of spread of material over time. If you remembered in calculus, you saw that the first derivative of a function essentially gives you the slope. It tells you whether the function is increasing or decreasing. That's what we saw essentially with the Nabla operator. And then if you take the second derivative of a function, then it can inform you about the concavity of the function. So it tells you whether, inform you of the rate of increase of that function. So it's really kind of the same analogy here. Studying the Laplacian of a vector or a scalar field really informs us of the rate of change of that quantity over time, or the diffusion, the spread, the rate of spread of stuff in the field. So for a scalar field, the Laplacian in Cartesian coordinates, so the 2f is just the second derivatives of the function with respect to each component, del 2f del z squared. If you are in cylindrical coordinates, that would be, so del f is the same thing as this. There should be no confusion here. So that's 1 over r d dr of r delta f by delta r plus 1 over r squared delta 2f by delta theta squared plus delta 2f by delta z squared. And if you're in spherical coordinates, it's a bit more complicated. So Laplacian of f is going to be 1 over r squared d dr r squared delta f delta r plus 1 over r squared sine theta d theta of sine theta delta f by delta theta. It's very similar to what we saw before, r squared sine squared theta d2f by delta phi squared. So these are the expressions of the Laplacian in each coordinate system. And then if you are dealing with a vector field, then you would have to apply this for each component of the vector field. Meaning, for example, that if we take f in Cartesian coordinates, which has fx, fy, and fz, then the Laplacian of capital F is going to be the Laplacian of each of these coordinates. So essentially you would be applying this. So you're going to have this for each of these. Okay. So here are really the main operators that are used in mathematics. They are very, very useful in physics, probably in chemistry too, I don't know. And they are very useful in physics, especially because we use them as tools. For example, in Maxwell's equations, you know, they appear a lot, and they enable us to understand the propagation of electromagnetic waves, of fields in fluid dynamics too. They are very useful because they enable us to study the evolution of a fluid over time, whether there is turbulence, whether it's laminar flow, and so on. So hope you find all this useful. If so, drop a like, and then subscribe, and feel free to add a comment. And then I see you in the next video to talk about another interesting topic. Until then, remember that physics is the belief that a simple and consistent description of nature is possible.